Okay, let's work example 1015 on page 315. And here's the problem. Right here it says, consider two cylinders having different masses M1 and M2 connected by a string passing over a pulley as shown in the figure. The pulley has a radius of r and a moment of inertia I about its axis of rotation. Let's see. The string does not slip on the pulley and the system is released from rest. Find the linear speeds of the cylinders after cylinder 2 descends through a distance h and the angular speed of the pulley at this time. So I've set it up here. Oops. So here is our problem. And this has a radius of r, rotational inertia of I. We have M1 and M2. We can say that V initial equals 0. It starts from rest. And we want to know what is the final velocity of these masses and what is the angular velocity of the pulley. Okay, so let's go ahead and solve that. Okay, let's zoom back in. Okay, come on. All right. So the thing I notice here is that the only force for here really doing work is is gravity. You have gravity pulling this thing down. Gravity is giving this velocity, and this angular velocity. So I could say that there's really no mechanical energy is not dispersed into the environment. We're not adding mechanical energy to it by any non-conservative force. So what we can start with is that E initial equals E final. And once you recognize that, now it's just an accounting problem. Where is the energy at the beginning? Where is it at the end? Okay, so where is it at the beginning? M2 times G times H. It's all in the gravitational potential energy of this guy. Equals, well, this guy, M1 is going to be lifted up. And it's going to be lifted up as much as this one went down. Doesn't that make sense? Right? If this falls down H, this goes up H. So this now has, M1 has gravitational potential energy now. But both of these objects have, this has kinetic energy, 1/2 mv squared. Whoops, what am I doing? And this has energy. And this has rotational energy. Okay. Now, if I want to know the speed, V, of all this stuff, I gotta solve for it, and I gotta get rid of omega. So, because the first thing we're going to solve for is V. So this is pretty messy. But one thing to notice, the speed of M1 and M2 are the same. So I can combine these. So that's one thing I can do. I can also notice that this omega is related to the linear speed of these guys. Key point, pay attention. When you got a pulley wrapped around the outside of this, the linear speed of this guy, of these masses, is directly related, like rolling motion, to the rotation of this guy. So, and that relationship is omega is equal to V over R. And then that's going to be squared. So this is going to get ugly. This is going to get ugly. We have to take this expression and solve it for V. First, I'm going to do a couple things. I'm going to bring this to the other side, and I'm going to factor out v squared from this big long expression here. So let's do that. This becomes m2 minus m1 times gh. When I bring that over the and I factor out the g and h, equals, and this is going to be 1/2 m1 plus m2 plus 1/2 I over r squared times v squared. You follow that? That makes sense? I just did 2 algebra steps here to save a little time. Oh, this should be a plus right here, huh? Yeah. Now I'm just going to solve for v. So v is equal to, well, m2 minus m1 times gh divided by, well, here I'm going to divide by this. I can factor out the 1/2, so I would have a 1/2, but that would come up as a 2 over here. And then I would have m1 plus m2 plus I over r squared, and then we're taking the square root of all of that. Now I can't see any other way to reduce this down, so this should be my answer, or something close to it. This should give me an expression in terms of the masses, in terms of the height, in terms of the rotational inertia and the radius, and in terms of the gravity field I'm in, of how fast this thing is moving after it's descended h. Oh, let's check. Where's my book? Oh, yeah, that looks about right. Now you might think to yourself, this is such an ugly answer. How can this possibly be the answer? I mean, a lot of the students psych themselves out and they go, oh, this can't be right. Yeah, it's right. Sometimes the universe is kind of ugly. Okay, or things, Now, if you were plugging in values, you would get an answer. You would get, 1.3 meters per second. But this is actually more useful. Because if you made let's say you made a spreadsheet or something like that, you would be able to plug in any value of mass and height and radius and rotational inertia that you wanted, and you get the answer. And notice something. What would happen if M2 had less mass than M1? What would happen in this expression? Well, it can't, because look at where it's starting. You would get, if M2 was smaller than M1, you would have a negative quantity here, wouldn't you? Yeah. Yeah, you get an imaginary answer. And we live in the real world, people, not the imaginary world. So, in other words, that doesn't work. This will only work if M2 is greater than M1. And it kind of says that in there. Now, to get to answer what omega is, that's pretty easy. Omega is just equal to to V over R. Okay. Do you understand that? V over R is the angular velocity of this thing? Because what is V? V, if this thing is moving down at, 2 meters per second, that means that the linear speed of the objects all around this pulley are moving at that same speed as this is moving. Okay? You need to kind of see that in your head. little cartoons. Okay? And so all we have to do is take, so omega is equal to 1 over r times the square root of 2 m2 minus m1 gh over m1 plus m2 plus I over r squared. And I don't think there's any way to reduce this down any further. And that is the answer that the book has. So yeah, that is it. Here's the whole problem. Big picture. Big picture. Conservation of mechanical energy. Okay? This guy right here. You need to be able to look at this situation and say, okay, nobody's adding energy to this system. Nobody's taking energy away from this system. We're just within the system itself. We're taking gravitational potential energy and turning it into kinetic energy. The only thing that's different now is that this pulley now has a significant amount of the kinetic energy. And another big idea, if you have a pulley rolling around here, you have to recognize this, that the angular velocity of this wheel is equal to the linear speed on the outside times or divided by the radius. You need to know this and you need to know this in order to solve this problem. You needed to know this so that you could make this substitution in here, that omega is equal to v over r. Otherwise you can't solve the problem. So this is the relationship between linear and angular quantities. Yes?
And just so I can better understand omega, what units go with it?
Okay, excellent question. What units go with omega? Omega is equal, well, units, is really radians per second. Now, sometimes they'll write it as seconds to the -1 because a radian doesn't have any dimensions to it, right? It's the arc length divided by the radius of a circle and you get an angle. So it doesn't have any dimensions, but it's still kind of there. And here's one way to think of a radius. Think of a radius, like the radius of a circle. Like if you say r is equal to, let's say this was 0.15 meters, 15 centimeters. A lot of times we just write, okay, the radius is 0.15 meters. But think of it this way. Think of the radius as 0.15 meters per radian. Meters per radian. The radius is how many meters you get if you, if you have a radian. It's the arc length you get if you go 1 radian, if that's your radian. Remember, here's a terrible circle. And if I take this radius and I take it and, oops, I'm off screen. And I take this radius, right, and I wrap it around the outside here so that this R and this S are the same. If S equals R, you have 1 radian. Okay? So you can kind of think of the radius as how much arc length you get per radian. Very useful way of understanding that.
And then RPM is also a very common one.
Yeah, yeah. We have to go from RPM to radians per second and all that kind of stuff. You have to be able to do the unit conversions. Okay. All right. We've beaten this one to death. That is all.